All right, so let's talk about a couple of these. So when you get to question number 3, with the sack of grain being lifted up, okay? And again, when in doubt, set up a chart. And go, okay, what types of energy can
Wasn't this from 2 days ago?
you have? So, like if I just drop my pen, you can have UG, you can have kinetic, and then you can have the sum. So today we're also going to introduce into this mix the energy stored in the spring. Okay, so then you're going to have a third potential type of energy. So here's the deal. So if you look on number 3, you got a 98 Newton sack, hoisted to a storage room 50 meters above ground. How much work is required? Okay, so here's the sack of grain. You're going to lift it up 50 meters, which is quite a ways. Okay? So you do that. That work that you're going to do is going to increase the gravitational potential energy of the system. Okay, you're exerting a force over a distance to lift that grain. So once it gets up there to the top, it's all potential energy. So the work that you do is stored as potential energy up at the top. There's no kinetic energy because it's just sitting up there. So here's what's most important. Once you get that number, and remember this today, even when we start dealing with springs, if you ever have one pure type of energy, whether that's pure energy stored in the spring, that's pure energy stored as gravitational potential, it's pure kinetic energy. If you can ever isolate a system where it's all just one type of energy, then you know what that constant has to be, because then you're just changing forms. So what you should see is that's 4.90 times 10 to the third joules. So that's that constant. Okay, so that's the work that's done. That's how much energy that you're going to do. Because if that answer is wrong, everything is going to be wrong. Okay? Everything is going to be wrong. So when you get to question C, when I ask you what's the potential energy, the kinetic energy, just don't write down 2 numbers and think I'm going to know which one they are. Make sure you tell me, hey, this is the UG and this is the kinetic energy. Okay? Just do not write down 2 numbers and think, oh, Bergkamp will know what that means. No, Bergkamp won't know what that means. Louis.
Just a question. What does KT stand for?
Translational kinetic energy.
Okay.
You can also have R, which is KR, which is rotational kinetic energy, which we'll get into after Thanksgiving. Pop?
Okay, so on the way up, what if you ask, like, if you ask the question, what is the potential energy at the, like, 30-meter mark on the way up?
Mm-hmm.
There wouldn't be any, would there be any kinetics at that point?
No, not if you're just holding it. But here's the difference.
So on the way up, how would you find, like, while you're raising it, the kinetic energy?
I would have to tell you how fast it was being lifted.
Okay. At that point?
Yeah. I'd have to say it's being lifted at 2 meters per second or something like that.
And then you just, like, put that, for the potential, you just put that height in?
Yeah.
Okay.
But here's what Pop asked is, like, what if it's being lifted up? Problems never play out like that.
Okay.
Problems always play out where you dropped it and you're calculating the potential energy and the kinetic energy on the way down. It'll never be the kinetic energy on the way up. Unless you know, the only way I would do that is if I say, hey, I'm going to throw this ball at a certain velocity, and it's going to be all kinetic energy here. And then I might say, okay, at the 2 meter mark, how much potential energy does it have? And then how much kinetic energy would it have?
Okay.
But that's based, but there's no outside forces on it. That's just based upon that dynamic between your potential and your kinetic energy. Okay, does that make sense? Okay. All right. On number 4, okay? Because if 4A is wrong, you don't get the whole concept. So what's happening on 4A is we're saying, here's this graph, and this is just a force distance graph, okay? Now, when you'll see this today once we get into springs. Springs gets weird because the farther you stretch a spring, the more force that it requires. This is why I just told you the average amount of force, okay? It's just a horizontal line, okay? So now, there's more force at the end, there's less force at the beginning, but we're saying on average, are you just like the snack king?
Yeah, it's wonderful. I like sitting next to him.
I mean, I'm sitting here going, it's just like you're a mom with pulling out random snacks for the kids.
Give me with some steaks.
I mean, there's pencils,
There's Fanta, there's Talkies.
I mean, seriously.
Snakes.
Well,
I'm
most
I'm
of
just
it.
waiting for you to walk in with a trench coat going, hey, you want a Rolex watch too? You know?
I can see that.
So, I didn't draw my graph as I drew it like this, but I went above 201.
No, I told, no. It has to be a horizontal line, okay? Because that's how you calculate the work that's done, because that's how much potential energy that you store.
But I thought it was 1/2 pH.
That's why I said, on average, this is how much force you exerted, and that's why it's a horizontal line.
Recording, Kaylee.
Sorry.
I-
Hey,
She
wait, can I
walked
finish
us.
this in here because I forgot to do it?
Yeah.
Pencil?
Ken?
I use them.
Okay.
Those on Mrs. House.
I didn't say a word. I didn't see anything.
I'm blind.
Okay. Didn't see a word. I was in the zone.
You're pretty.
Okay.
What?
So, what's going to happen on 4B is that the work that you do, which is the energy underneath this curve, or is the area underneath this line, is the potential energy that you store in the spring. You let go of it, that energy all becomes kinetic energy at the point that that bow leaves, or the arrow leaves the bow. So if all goes well, your answer to 4B should be around 40 meters per second.
What is
Great.
Wait, what was it?
4B should
4B should be around 40 meters per second. So you're going to take that work, set that equal to your change in the kinetic energy, which is K minus K naught, but it has no initial kinetic energy to begin with. So then your kinetic energy is going to be 1/2 mv squared. So that area equals that kinetic energy. So for your velocity. Your height should be around 90. Because then what's happening, you're taking all of that kinetic energy that it is when it leaves the bow, and it's all stored as potential energy up at the top. Okay. Here's what I want you to visualize on number 10, or number 5. This is what we talked about. So, on number 5, here's the setup. So, you've got a ball. You're going to throw it down. You're going to throw it down, okay? So, because you're throwing it down and you're not dropping it, what two types of energy does it have? Potential and kinetic.
What's up, Lewis? You ready to finish this test?
Okay. So, now, here's what I want you to get out of this. Is that because you're going to throw it, and kinetic energy is a scalar quantity, it doesn't make any difference which direction I throw it. Okay, because you can't differentiate it. When you look at how you calculate kinetic energy, that's just 1/2 mv squared. Throw it down, throw it horizontal, throw it up, throw it at a 45-degree angle, doesn't make any difference. Okay? The direction that I throw it does not change the amount of kinetic energy that it has at the top. So this is where the magic happens. So, and this also plays out on one of the problems on when you get to
5.
28 out of the book. So, problem. So when you're up at the top, you have UG and you have kinetic energy. And that's going to the sum of those two is going to equal the final kinetic energy at the bottom. Okay? So I throw this thing down. It has UG because it's above the ground. It has KT because it's moving. And then when it lands, the sum of those two values is pure kinetic energy. So here's where the magic happens. Oh, that's MGH. That's 1/2 m v naught squared. And that's 1/2 m v squared. Well, conveniently, what's going to happen to the masses?
Cancel.
I'm also going to multiply by 2 to get rid of that fraction, so I get 2gh plus v naught squared equals, otherwise known as
That equation.
that equation. Okay? So that equation comes from the law of conservation of energy. Okay?
That's cool.
Now, this is where it works. Let's just say I drop it. Okay?
I did drop it.
If I just drop I just dropped my hydrogen. If I just drop it, what happens to that initial velocity part?
Cancel it out.
Cancels out. So then the final velocity is only going to be based upon your potential energy, which is that 2gh part. Okay? So that equation comes from the conservation of energy. Okay?
Yeah.
Cool with that. On number 6, every answer should start with a 1.
Get it.
Great.
Get it.
Okay?
Are most of them kind of the same answer?
Yes.
Yay.
Lewis likes
And your answer to C should be something around your age.
Cool.
You're almost 19.
Ish. It's an ish. Okay? Something around your age.
What about 17.8?
Okay, now let's talk
17.8.
about
For E?
problem 20. Okay?
No, C I got 18.
Okay, 0.7.
So I want to make sure everybody's
Oh,
cool with what's
17.9.
happening on 20. So you got a wrecking ball, 1,000 kilograms, quite a bit. You got a cable that's 15 meters long. It's pulled back to an angle of 25 degrees. How much does the gravitational potential energy of the ball change? Okay? So you want to find the change in UG, which is mg delta h. So what are you going to assume the initial height of the wrecking ball is? 0. Don't make this difficult. Okay? All right? So that's going to be h minus h naught. So if you're clever, you're going to let h naught equal 0. So what you have to figure out is that height. So that's where you've got to use that 28, excuse me, 20. That's where you've got to use that mgh, but you have to calculate that h, and that's going to where you're going to use that h equals L times L cosine theta. Or if you want to rewrite this, you could write it as L times 1 minus cosine theta. If you want to factor it out, it's the exact same equation. Okay? So anyway, so that answer to number 20 in joules should be something times 10 to the 4th. Okay?
Louis?
What?
Now, when you get to question 32,
Did you do that one?
there's a couple of ways you can tackle question number 32.
Sorry. My bad.
The book
making-
gives answers in kilojoules.
Yeah, it's just,
Getting
Well, I know
on
how to,
there.
like,
Shut up.
convert it.
yeah.
Did you do the green sheet?
It catches your car every time.
At least it doesn't do like pico
Did you do the
joules.
green sheet?
Weird about that. Okay? So here's the story on 32. Let me kind of give you this visual. So here's this hill. Okay? Now, so this is 5 meters high, and you're told that it's, here's your car.
It is hot.
I'm sorry.
So we've been toasting here, Mr. Burkett.
I thought I've been cold all day.
No,
I
you're
wish.
cooking with
Look
heat.
at him. He's wearing 3
You're cooking it
layers.
up in here.
That's why I've got that heater going.
I haven't
'cause
taken.
I've-
You've got a heater going?
Yes.
Oh
Are
my!
you okay? You might be sick.
Dude, I am- I'm-
No, you
I'm-
thought it was cold too, didn't you?
A little bit.
Yeah.
No,
I was
fine
heat
now.
sick.
Okay.
It's hot, bro.
I'm getting the tingles, Mr.
I had to
Burkett.
take my
Get
jacket
over
off.
I'm just
I haven't
wearing a
taken it
hoodie.
off all day, and I had to take it off.
Okay.
I need to take my.
So here's the story. So when the car is rolling, what's the only type of energy that it has? Kinetic.
Kinetic.
That's all it has is kinetic energy. So one thing that you could do to determine if it makes it up the hill is take all of that kinetic energy and say that's 1/2 mv squared, and say, okay, if that translates all to gravitational potential energy, and set that equal to MGH. Solve for that height. If that height is above 5 meters, it makes it. Okay?
Cool.
If it doesn't, now the other thing that you could do is you could figure out how much potential energy that it has at 5 meters using MGH. If that number is less than the kinetic energy that it has at the beginning, it makes it.
Your goal.
Okay? So there's a couple of different ways you can view that problem.
Oh, I get it.
I see.
Now, when you get to 32, if your answer to part B is yes, which it should be, okay, it makes it up, then what's the car's speed after coasting down the other side? So it's going to make it up the hill, it's going to go to here, and then it's going to come down like this. Now, clearly, what does your answer to 32B have to be greater than? 10, right? Because if it just went back to the initial height, it would go back to 10 meters per second. So again, there's a couple of ways you can do this. You can sit here and go, okay, well, it's basically going to fall 10 meters, right?
Yeah.
So if you know how much energy it still has when it gets to the top, and you can add that to the UG that it's going to get when it's coming down the hill, or you can say, the other option is that you realize it's going to have the same amount of kinetic energy when it crosses that 5 meter threshold, and then add to that the amount of UG that you're going to gain from falling 5 meters, get that total energy, solve for your velocity. Okay, so your velocity on 32 should be between 12 and 15 meters per second.
That's what I got.
On 28, 2 of your answers should be in the 20 range, and 1 shouldn't.
The second 28?
Oh, problem 28.
Okay.
They should be in the 20 range?
On problem 28,
Probably around like 27.
2 of your answers should be in the 20 range,
Okay.
and 1 should not.
2 of them should be in the 20 range.
Yes. 2 should be in the 20 range.
Ooh, why do you always have 2 big?
On the multiple choice
I
part,
got to floss my teeth after lunch.
you should have no answers of B.
Perfect for that.
You don't like flossing?
What?
On the multiple choice part, you should have no answers of B.
Little wires on the back of my teeth, and I literally
Okay.
can't get a wire.
I have a lot of
out
one
because they're-
Huh?
I have a
they
lot
run
of
all the way
one
across the back.
Well, that's
Yeah.
fine. It's this part.
Yeah.
Can't-
They, for
Get
some
the
reason,
plaque
they
off
like
my
that
teeth.
letter. I don't know.
Respect.
Okay.
I can't
That's
stand
why you're able
doing
to score really good if you only answer C on test.
Well, this particular one. All right. Any questions?
No.
Going once?
Can you get me started on 28?
Kidding.
I have the
Don't
chart,
even get started.
which I think I know what I should do now. Probably.
Okay.
28.
What's it going to start with? Potential and kinetic, right?
Right.
So what I would, this is how I did 28. I said my UG plus my KT, right? So then on 28, it's going to say ball is 20 meters, say, using concept, ball's maximum height above the ground. So when I add those 2 numbers together, what's that going to, when it reaches its maximum height, what's the only type of energy that it's going to have? UG. So I'm going to call that UG prime.
Ugh, prime.
So
It's like Optimus.
that MGH plus that 1/2 mv squared has to equal the new MGH.
Okay.
Prime.
Okay.
M's cancel.
Does that make sense?
Yes.
Okay. And there's a reason that they never gave you the mass of the ball.
I know. It just stressed me out.
I know. If you want to make it easy, then make it 1 kilogram.
Okay.
Well, I'm serious. I mean,
It works.
it works.
It works.
It all works. Okay. Anything else? Going once? Twice?
So,
So there was like on the crane problem on the assignment that I just gave back.
Yeah, the first question.
You're good.
Okay.
That's lots.
All right. So now here's the next thing,
oh, this?
which is going to be springs. Okay. So the cool part about this, and we'll do lab with this tomorrow, is that it harkens back to the very first lab that you all did in this class. Very first lab that you all did.
I wasn't here.
Yes.
Okay, well, this will be, okay. So, you took little weights and you hung them from the spring and you said, ooh, it may stretch us at a certain distance, right? Okay? And I said, oh, you take the mass and you multiply by 9.8 meters per second squared, and you said, okay. Well, we didn't know what the number meant or where it came from, okay? But now, here's the cool part of this, is now it's kind of become full circle. So, here's the deal. When I take this 0.2 kilogram mass and I hang it from the spring, is work being done?
I
Yes.
mean, it's kind of balancing.
What?
Yes.
Yes.
Yeah.
Why is the work being done?
Because it is applying, because it's deforming the spring, and that takes energy to do that.
Applying force.
What's the simplest way to calculate work?
Force times
Force
distance.
times
Is there a
distance.
force acting over a distance?
Yes.
There you go.
There we go, Sam.
Okay, work's being done. Now, if I put a half a kilogram mass on there, what's going to happen to the amount of work that's done? More or less?
More.
More. Why?
More force.
More force
distance.
and
And more distance.
more distance. Ooh, that's kind of cool, right?
But it keeps.
So, what we're going to look at
So it
Still
keeps
moving.
stretching more.
is that we're going to draw a graph, and we're going to put force on the y-axis and elongation on
Or energy.
the y-axis. Now, when you all did this very first lab, you actually put force on the x-axis and elongation on the y-axis, because force was your independent variable and elongation was the dependent variable, okay? The units won't work out if you do it this way. So for the units to work out in terms of energy, you've got to put force on the y-axis and elongation on the x-axis. So, will this graph go through 0, 0?
Yeah.
Yes.
Yeah, because if there's no force, guess what?
There's no
No.
elongation.
No elongation. Now, you have to remember, this is the elongation of the spring. This is not the length of the spring. It's the elongation of the spring, right? So, let's say, for example, a 20 Newton force, just to make up a number, stretches a string 0.20 meters. Now, this is what's known as Hooke's law,
That's a hefty stretch.
which means that this is going to form a linear function, okay? So here's the deal. When you look at this, we're going to look at this in terms of a linear function, y equals mx plus b. So what's my y-intercept going to be?
0.
0. Okay, it's Hooke's law. No force, there's no elongation, right? So we need to find the slope. Now, in this situation, I got 20, and I got 0.2, and I got 0, and I got 0. So what's going to be the slope of this line?
100.
Why?
Because it's force over elongation.
Yeah, so if I take 20 newtons and divide that by
What?
0.2 meters, first off, what units do I get?
Newton.
over
No,
meters.
kilogram second squared.
Don't make this difficult.
Oh, Newton.
Newton meters.
No, we acceleration.
It's kilogram
Do I
second
get
squared.
Newton meters,
Oh wait.
or do I get newtons per meter?
Newtons
Per
per
meter.
meter.
My bad.
Newtons per meter,
Oh,
okay?
My bad. No.
Because Newton meters,
All right, these units are.
oh, stay with me here.
I'm losing.
Oh, believe me,
He's
we haven't
losing
even begun to get into jacked up units yet. We have not begun to get into jacked up units. You wait until we get into electricity and magnetism.
Oh, no.
That's some seriously jacked up units.
Oh,
Okay, well, save that for another day.
okay.
Next.
So, notice this is not Newton meters, okay? Because if it was Newton meters, that would be
Work.
joules, right? Which would be work, which would be energy.
Which would be
So
power.
not Newton meters, it's newtons per meter.
Per meter.
Which is different.
Different, completely different.
Completely different.
Distant cousins at
Same
best.
thing.
Now, numerically, the value of this, if you take 20 and divide it by 0.2, you get 100. Now, here's an old school way to show that these numbers are significant. Put a bar over the top of it. So sometimes when you look at science books and you see bars over the top of zeros, that means that those numbers are significant. It's just like saying, hey, here's a little freshman. He's cool. He's with me. Like you put your hand over the top of him and go, he's with me.
We don't like these
like
We wouldn't do that though.
Okay?
We don't like the freshmen.
There's
I
no
don't either,
freshmen.
but sometimes I'm just saying.
There's
It's
that
just the
one.
analogy
There's
that I
a
had.
unicorn.
There's that one.
Unicorn.
Now, this is what's known as the spring constant. And that changes based upon the type of spring. So this is not like a universal constant. It isn't like every spring in the world stretches the same amount for every force that's applied to it. So if you think about this, the bigger this number is, the farther it's going to stretch, because it's like force per unit of meter. So if that's a really big number, that means if you have to apply a lot of force to it to get that thing to stretch 1 meter. So when you look at this, I don't want you to think that, oh, every spring has a same spring constant. It changes depending upon the structure of the spring. Now, at this point, we have y equals my spring constant, which I'm going to put as k, times x. Now, what's graphed on the y-axis?
Force.
Force equals kx, right?
Yeah.
Cool with this? So, when you look at a force calculation involving springs, all this is a linear function. It's just y equals mx. K is just the slope. You're graphing x on the y-axis, force is on the y-axis. Okay? If you see F equals kx, it's just a graph. K is the slope, x is graph, y is on your force, that's all it is. And this is just going to be your spring constant. Cool with that?
Yep.
Okay. Now, here's the deal. We're going to go up here, we're going to go back to this graph. We're going to have force here, and we're going to have elongation here. Okay? Now, since this is a force distance graph, okay, could you find the area underneath that graph?
Yes,
And what do you think that would represent?
that would represent joules.
Which would represent,
Meters.
which would represent
Work.
work.
Okay.
Okay? So the area underneath this graph is going to represent work. Okay? So how are you going to find the area underneath this graph using geometry?
1/2.
Wouldn't it be
Base and height.
Area is going to equal 1/2 base times height. True?
Larry?
True? And the area is going to represent work, right? So that's going to be 1/2 my base, which is going to be my x, and the height is going to be my force, right? Okay?
Also equals.
Okay?
What?
Now, here's what's different. And this is what's different from the problem that you all did on the assignment. On that problem, I said, look, on average, you're going to exert 200 newtons of force. Okay? And that's why we drew it as a horizontal line. And we treated it as a rectangle, and we said, oh, force times distance equals work. In reality, when you have springs, it's a triangle. Okay? So now when you find that work, okay, that's going to be 1/2 Fx. Okay? So this is going to be 1/2 Fx, which is not a triangle. Okay? Got this idea.
Yes.
Now, here's the whole kicker to this. Up here, we said force, we're going to do a little bit of substitution. We said on a linear function that F equaled Kx. True?
Yeah.
So I'm going to take this Kx and I'm going to put that in here for this force. Okay, all I'm going to do is that substitution. So I'm going to have 1/2 times Kx times x is going to equal work. Well, that becomes what? 1/2
KX squared.
kx squared, which is going to equal work, which is also going to equal the change in us.
Us?
Changing the
isn't that
amount
just
of energy
kinetic
stored
energy?
in the spring. Okay, so this is energy stored. So
no,
us
it's
is changing
potential
energy
spring.
stored in the spring. Okay, so and if you think about it, that makes sense. So the further I pull this thing down, what's going to happen to the amount of energy that I store?
It's going to increase.
Yeah, it's going to increase. So if I double the distance that I stretch it, what's going to happen to the amount of potential energy that I store?
Quadruple.
It's going to quadruple. Right now, let's look at the units. Okay, here's where the magic happens. K is your spring constant. So what's the units of K? What are the units for K? It's your spring constant. Newtons per
Meter.
meter. X is your elongation. That's going to be meters squared. So if I take newtons per meter times meters squared,
Newton meters.
I get
Oh my
newton
God.
meters, otherwise known as
Work. Joules.
joules.
brother.
Okay? So that's why I said what you cannot do when you set up this graph, this is why you have to put force on the y-axis and elongation on the x-axis. That's the only way the units work out to get joules out of that equation. Okay? All right. Now, if you are a calculus nerd, which some of you are,
We need to be told.
so we have a linear function of f equals kx. True? Right? Linear function. So you can write this then as the integral between 0 and 0.2. So you're going to evaluate this over this integral of 0.2. And you can write it as kx dx if you really want to get fancy, right? So you
Too
take
far.
that, then you take,
I haven't gotten this far.
okay, well, when you take the integral of that, that becomes 1/2 kx squared. Boost the exponent by 1, put the fraction out in front. So now when you evaluate over that interval of 0.2, you're just going to get that area. So at some point when you study calculus, you will learn that the area underneath a force distance graph gives you work, which is your change in energy. Okay, so at some point you all will learn that. Just there's your precursor. Okay, so how this plays out. Let's say that how much time we got? Okay,
30 minutes.
so I'm going to take this cart, and it has a plunger on the end of it. And that plunger has a spring constant of 3.00 times 10 to the third newtons per meter. Okay? And this thing has a mass of 0.3 kilograms. And it's moving at 2.5 meters per second. Okay? So imagine here's my car. Okay, this thing is rolling along. Okay, right? Y'all have done labs with this, right? So it's going to hit the wall. So what's it going to do when it hits the wall? What's this plunger going to do?
Compress.
It's going to compress, right? So what's going to happen to the kinetic energy that I have here once it hits the wall? Kinetic energy is going to decrease. Oh, it's going to turn into what type of potential energy?
Spring. Us.
Change into us. So KT is going to change into
US.
us, right? Now, if I throw it up in the air, the kinetic energy is going to change into O. So, now, it's the same idea though. If I give it 5 joules of kinetic energy, how much gravitational potential energy will it have at the top? 5. So if this thing has 5 joules of kinetic energy, when the spring is fully compressed, how much us is it going to have?
5.
5 joules.
6.
So it's the same idea. So you can think of the spring as being like horizontal gravity. It's like, oh. But if you think about it, it kind of does, right? So you're going to take kinetic energy You're going to store it as potential energy. Mother Nature doesn't like potential energy, so what's she going to do? Change it back into kinetic. If Mother Nature liked potential energy, what would happen? You'd hit and it would just stay, which would be really weird. Okay? But she doesn't. She likes energy of motion. So here's what we're going to do.
She doesn't like us.
So this thing is moving along, right, at 2.5 meters per second. So we're going to compress the spring 0. I got to remember these numbers. 0.1 meters. Okay? So imagine this. The cart's rolling along, and we're going to compress that spring 1 centimeter. Okay? Like this. So what I want to know is ultimately how fast is it going at that point? How much kinetic energy does it have? And how much potential energy does it have? Okay? Now, think this through. We're not going to have UG in this case. We're only going to have, on this chart, what are the only types of energy that we're going to have?
KT.
We're going to have KT and us and the sun. Okay? So initially, we're just rolling along, right? We're just rolling along. So if we're just rolling along, what's the only type of energy that it's going to have? KT. Do we have enough information to calculate the kinetic energy of the cart?
Yes.
Yes. So we can calculate that initial kinetic energy by going 1/2 mv squared. True?
Yes.
So let's get that number. So we've got 1/2 of 0.3 kilograms times, what do you say, the velocity, 2.5 meters per second
0.938.
squared. What'd you get?
0.938.
Okay. So 0.938 joules. So if you're into the container analogy, this container, my kinetic energy is filled up to 0.938 joules. Okay? So that's the maximum amount of energy I can have in this system. Okay? Can't have any more than that. So since the spring hasn't hit yet, how much us do I have?
0.
0. Okay? So that means the sum is going to be 0.938. So that's why I said if you screw up this first calculation, everything else is screwed from there on out. So what you want to do when you first set up this chart, you should be able to identify one pure type of energy. It's all potential, it's all kinetic, it's all gravitational, it's all us, it's something, okay? So typically how these start is that you have one pure type of energy. Okay, now visualize this. This spring has been compressed 1 centimeter, 0.01 meters. So what's going to happen to the amount of kinetic energy that I'm going to have after that's compressed 1 centimeter? It's going to decrease. What's going to happen to my us?
Go up.
It's going to increase, but they still have to add up to
0.98.
0.938.
Oh,
True? Still have to add up to this number. So since it's compressed 0.01 meters, and we know the spring constant is 3,000, what can I calculate? I can calculate us. Now, what does my calculation of us have to be less than?
0.938.
Yeah, I can't, if I do this calculation and I get 1.1, it's like, whoa, we have created energy. Okay? So when you get that, step back and look at that answer and go, oh, hey, does this make sense? All right? So we're going to have 1/2 my K value, which was 3.00 times 10 to the third newtons per meter times 0.010 meters squared. Don't forget to square that distance. That's the most common mistake that's made. You forget to square that distance. So how much us do you have? 0.15
Yes.
joules. Okay? So that's how much us I have. So at this point, I've compressed it 0.10 meters. I have 0.15 joules of us. So how much kinetic energy am I going to have?
0.92.
Yeah.
How'd you get that?
Subtraction.
Yeah, if I subtract that, you get what?
923.
0.923? Because everything still has to add up to,
0.938.
Wait, that is not.
okay?
Yeah, it should be 0.79.
Yeah, okay, that sounds better. It's like, that's not much.
Not much compression.
So 0. Point what?
0.788.
That's not what's going on.
788?
Yep.
Was.
Okay,
It wasn't. It wasn't.
cool with that. Now, how can we use that to calculate the velocity of the cart?
It's a great question, Mr. Burkett.
K
It's
equals 1/2 mv squared.
Well, kinetic energy equals 1/2.
MV squared.
You know the kinetic energy?
Yep.
So the mass.
2K over M's rooted.
2K over M, rooted.
Yep. Rooted.
Root for it, baby, root for it. So you got 2 times 0.7. I've taught for a long time. I've never heard anyone say rooted.
Why did you say rude?
Cause I don't know.
I like it. Rooted, man. Rooted.
You're gonna root it.
Give me a root. Okay? And the mass is point.
Bergen, have you put
Berg, you
meters?
put meters for a joule.
Oh, whatever.
Hey.
Newton meters.
His mind's not
joules.
on it.
It's all it's what's
Joules
the
per
units
meter,
between
man.
friends.
That's
Okay, so what do you get
Meter
for
per
the
kilo.
velocity? What does your velocity have to be less than?
The original.
Yeah. So what do you get?
2.29.
2.29
Yes.
meters per second.
Joules per-
Okay? Got the idea.
You
It's
can
the
do
same
one
type
in
of
joule per
thing we
second.
did yesterday when we threw something up in the air.
He spells it.
Okay? Now, here's the last question.
G-U-L. It's G-U-L.
What would be the maximum compression
Joules.
of the spring?
How far can it?
When that thing hits, what's the maximum compression I could have of that spring?
Set US equal to 0.938
Why?
because that's when all the kinetic has turned into potential.
Bingo. So when this thing is completely stopped,
He's in.
okay?
I was just gonna say.
When it's completely stopped, that's when you're going to have maximum compression, right? Okay? So then, at that maximum compression, you have no velocity, because guess what? You're going to do what? You're going to change the direction. When you
Bounce
change the
back.
direction, the velocity has to go to
Less tokens.
0.
Yeah, 0. Sorry.
Okay? Well, it eventually it'll go
Big
down.
Sean.
Okay? So at maximum compression, so if you go back up here,
He took an LSD.
so at maximum compression, how much kinetic energy are you going to have?
0.
0.
OJ.
OJ. How much us are you going to have?
938.
0.938.
0.938, because the sum is still going to be,
938 joules.
so you know that us equals 1/2 K.
X squared
So 2 us,
over K.
and then
Rooted.
root it,
Root it.
gets me X.
You say root it or
He said
rooted?
rooted.
Rooted.
Rooted,
Rooted.
rooted, same thing.
Rooted.
So I'm going to take 2 times 0.938. I hate this thing. Joules.
Get off my chair.
Now, I'm not going to divide by mass. I've got to divide by the
Constant.
spring constant, which is going to be 3.00 times 10 to the third
Got your foot rest.
newtons per
He's got a death
meter.
on it.
Now, if you do want to get, that gets a little bit weird because your joules, because that's like newton meters, okay? So then you could only go through that. Oh, that cancels out the newtons, and then that flips up. You get meters squared. That's why you get a distance of
meters.
meters. So what did you get?
He's unsure.
What, Pop?
0.025.
How did you get the spring constant?
I just gave it to you in the
Oh,
problem.
you did?
Yeah.
Oh, okay.
Yeah, I would have to give you
Okay.
that problem.
I didn't
Yeah,
know.
no, I get at the beginning when I was laying it out, I said,
Well,
Oh,
Probably.
that's the spring constant.
yeah,
probably.
Okay.
Good to know. I got 0.0.
Yeah.
Is
I was gonna say,
the
I
is
did
the
not
spring
know how to
constant the
find
spring rate?
He's not in this.
Well, it's just the
What?
slope of the launch. It's the slope.
it's just the slope of that force elongation graph. So what'd you get?
0.025.
This is a constant.
That's what I got.
Sweet.
So how stiff the springs? Spring.
Yeah.
Does it make sense that your answer is bigger than .01?
You stepped in.
Yeah.
Yes.
Yes, because at .01 you still had
Connect.
kinetic energy.
Bingo.
Okay.
You let your dog
Got
poop
it?
in the front yard.
Yeah.
What is this?
Okay.
You let your dog poop in the front yard.
So stop that camera for a second.
Really?
Well, let me say hi to Vitor.
You say hi to Vitor.
Vitor.
Hi Vitor.
Hi, Vitor.
How are you doing?
Have fun watching this lecture. You probably didn't even understand it.
Brought to us by Takis.
Not like you can even understand us. We're in 2 times.
Hold on, I'm gonna do a hang on. I'm gonna do a cool thing. Give me a second.
It's a harsh crowd.
It's gotta be.
I've been laughing all the time.
Hey, I felt my tongue.
Oh, can you see it?
Okay. So stop that up.
We said hi to Vitor.
Good transition.
Good transition.
Good transition.
Okay. So when you get to number 4, okay, I said make a sketch of the graph, okay? If you want to put that on graph paper, you can. If you want to actually draw it on your paper, that's cool, okay? But it does need to be to scale, okay? Now, when you get to number 6, so here's the story. When I typed this, I don't know why, a box of purple crayon sounded good, okay? So you got a mass, surface, hits the spring. So what's happening on number 6 is the reverse of kind of what I just did. So this is going to be moving along, and it's going to hit a spring that's attached to a wall, and you're going to compress the spring. Okay? So if you kind of get that visual. Now, when you get to number 7, Jerry the Mouse is on a skateboard, combined mass of ½ kilogram. Now, what's going to happen on number 7 is that you are going to combine all 3 types of energy. You're going to have a spring, and you're going to have kinetic, and you're going to have So on number 7, you are going to combine all 3 things. So you're going to combine a compression of us. He's going to roll along, and then he's going to move up the half pipe. Okay? So keep that in mind. What I would suggest on number 7 is that you set up that chart, and you're going to have 3 things. You're going to have us, you're going to have KT, and you're going to have us, and then you're going to have the sun. Okay? So you're going to have all 3 things on problem number 7. Now, when you get to number 8, here's the Zambezi River, and you're going to bungee jump off of it. Okay?
That's fun.
So, let me kind of lay out what's going to happen.
You hit the ground.
So, and I kind of take you through this, but you're going to fall 12 meters before the string begins to stretch. Okay? Right before the bungee cord does. So you're going to fall for 12 meters. You're going to be in free fall for 12 meters. At the end of 12 meters, then the bungee cord is tight, and then it's going to begin to stretch. And you're told that when you get done, you end up 31 meters below the bridge. So you fall for 12, you end up at 31. How far did the bungee cord stretch?
19.
19 meters, right?
Yeah.
Okay?
That's
So
good.
that's going to be that stretching thing. Now, so here's the deal. the first thing you want to do when you get to B is that you want to find the spring constant. So let me tell you how to think this through. Imagine that you're down here and you're going to get lifted back up. Okay, I've given you the mass. You know that you're going to get lifted 31 meters. So if you can figure out your UG, okay, that's how much UG that you have. So that UG that you have, imagine that you're just being lifted up through a height of 31 meters. So that UG that you have is going to equal the US that you're going to store in the stretched bungee cord. Okay? So that's what you're going to do. So this is going to be MGH, and that's going to be 1/2 K X squared. You're going to know everything but K. Your height is going to be your 31 meters, because that's the total amount of potential energy that's in the system, because you end up 31 meters below the bridge. The energy that you store in the spring is going to be K times how far you stretch it, and you're going to stretch it 19 meters. The only thing you don't know is K. So your value for K should be around 100, if you do that right.
Number 6.
What about it?
Is that what that was?
No, that was number 8.
Okay.
That was number 8.
All three
Okay,
of these
I'm done.
seven.
You're on your own.
Let's go.
So then we got a lab tomorrow, an African day on
What's the lab about?
springs.
Over gravity.
Like,
Ooh!
I'll be in their team.
Let's go to Africa.
Do you have more stories to tell us?
I'm gonna be gone.
I got lots.
You're always.
You're gonna tell us a bunch on Friday.
Yeah,
Tell
Well,
us
it's
your
also,
stories,
we're
Mr.
also getting a little
Burkham.
philosophical.
You were like.
So-
Philosophical.
Wow, what a terrible day to miss.
Soccer
I
team's
know.
out here.
I'm really sad about it.
He can't
See,
have
you don't sound
Corny.
You sound pretty happy that you're
devastated.
Vitor's gonna be back. Is Vitor gonna be back tomorrow or Friday?
If you want me to record